Okay, so we know about how to determine the end behavior of a polynomial function. We know about zeros, cross points versus touch points. All right. We also know that we may have a zero if the function changes sign in between two consecutive integers, that we might have a zero somewhere in between there if it changes sign. And now we're going to talk about turning points. Okay? This is a turning point. We can call that a relative minimum. This is a turning point. We'll call that a relative maximum. And right here also it turns back around, so we'll call it a turning point. Okay? And this one was also what we called a touch point in our discussion of touch points versus cross points, having to do with the multiplicity of the zero. Okay? Now, we'll want to know what are these turning points in between here and how many are we going to have? Okay? So, there is a little theorem that says the number of turning points of a polynomial function of degree n is going to have at most n minus 1 turning points. Okay? One of the really simple ones to think about is the polynomial function f of x equals x squared. Okay? You know that that's a parabola, and it might just be x squared plus 4x minus 9. I don't even know. Okay? But we do know that it is a parabola, and it only has one turning point. Why 1? Because n is 2, so n minus 1 would be 1. It's always going to be 1 less than the degree of the polynomial, and it's going to have at most that. Okay, it could have fewer turning points, okay, but that is the theorem about the turning points, so keep that in mind. All right, so now we're going to look at a strategy for sketching a polynomial function, putting it all together, okay? First of all, we're going to use the leading term to determine the end behavior of the graph, okay? Does it go up on the left or down on the left, and does it go up on the right or down on the right, okay? We also want to this should go quick. We want to find the y-intercept by evaluating our function at 0. Let x be 0 and find the y-intercept. Okay? Number 3, we're going to look for x-intercepts, and that has everything to do with finding the zeros of the function along with their multiplicities. Okay? Then we're going to put points on our graph for the x and y intercepts. And we're also going to lightly sketch the end behavior. All right? Number 5, we're going to draw a sketch, drawing from the left end behavior, connecting the x and y intercepts in the order that they appear from left to right using these rules. Don't forget cross points for zeros that have an odd multiplicity and touch points for zeros that have an even multiplicity. Okay? We might want to test our function for symmetry if it's easy. If we have an even function, a function that is symmetric about the y-axis, here is the test you remember. And really, what that's going to look like for polynomial functions is if that test works, that can only happen if we have all even exponents. Okay? If a polynomial function is an odd function, that's going to display symmetry about the origin. That means it will pass this test. F evaluated at negative x is equal to the opposite of our function. That will work if you have all odd exponents. But this one, you can have no constants. Because a constant, like if on the end it would say +7, okay, that is understood to be plus 7 times x to the 0, and 0 is an even, okay? So number 7 then, more points if you want a greater level of accuracy. In particular, to estimate the location of turning points, find several points between two consecutive x-intercepts. So plot more points. Okay? Now, on our first example, we're going to follow the guidelines to graph the polynomial function g of x equals x to the 5th minus 2x to the 4th. Okay, so recall that the first thing that we look at is we are going to look at end behavior. Okay? Not behavior, behavior. There we go. That looks a little bit better. End behavior. So to determine end behavior, we look at the leading term. Okay? The leading term is 1x to the 5th. Okay? So since this is an odd n, okay, but a positive lead coefficient, okay, it's going to be one tail's going to go up and one tail's going to go down. If you refer to your chart, okay, we're going to go up on the right, but it's going to go down on the left. Okay, anytime you have an odd exponent, but with a positive leading coefficient, it's going to be that behavior. Up on the right, down on the left. So keep that in mind. Okay? The second thing we want to do is find the y-intercept by calculating g at 0. Okay? G at 0 is 0 to the 5th minus 2 times 0 to the 4th. Well, g evaluated as 0 is just 0. Okay? We can put that on our graph if we want to. All right, so number 3 is to actually find x-intercepts, and that entails zeros and their multiplicities. So what we're going to do to find those zeros is we're going to take our function x to the 5th minus 2x to the 4th, set it equal to 0, and solve. Now this one we can factor out a common factor of x to the 4th, and when we write the leftovers, it's just x minus 2. Okay? Set each factor equal to 0, so x to the 4th equals 0, x minus 2 equals 0. And so we're going to have a 0 at 0, and the multiplicity there is equal to 4. Ooh, that means we're going to have just a touch point. Okay? And here for x is equal to 2, the multiplicity was 1. I should write that. That looks a little bit better. The multiplicity was 1. And so that means we are going to have a cross point there. All right, we already plotted our x-intercepts. I'm sorry, our y-intercept. And there is our first x-intercept at 0, and our other x-intercept is at 2. Okay? All right. So the fourth thing that we're going to do is it says to, okay, that is actually the fourth thing. We're going to plot the x and y intercepts, and we're going to sketch the end behavior. So what I like to do is come over here and copy that end behavior. It's going up somehow, okay, on the right, but down somehow on the left. Okay, and the rest of this clues us in as to how it does that. Okay, quick sketch. Kind of sketch it a little bit. Okay, then number 5, we're going to draw, you know, from left to right, a loose version of your graph, okay? So remember that this was a touch point and this one was a cross point. All right, so I'm going to come up here and I'm going to just touch at the origin. Okay, then I'm going to come down. I don't know how far down we need to go here. I'm not sure. Maybe I should find that out, but I do know I'm going to cross at the point 2, 0 and hook up with the end behavior here. So real loosely, that might be the shape of our graph. Now, this sixth thing we might want to consider, remember, is symmetry. And since we have a mixture of odd and even exponents, we are going to have no symmetry. This thing's not going to be symmetric about the y-axis or about the origin, either one. Okay? And then finally, the last thing we need to do, number 7, is more points. More points is needed. Okay? So I'm going to organize my points in x, g of x. Okay? Let's see. First of all, let me get the C off of there and the T off of there. And I hope you're working in pencil because we might be editing some of this. You know, I might want to know what happens for, on my graph, for x is equal to -1 and -2. I think that would be good when x is -1 and -2. I also want to know what happens when x is 1. I know what happens when x is 0, but I don't know what happens when x is 1. I know what happens when x is 2. My function is 0. Let me also do here 3. And that might be enough to get a little bit more accuracy. Okay? So g evaluated at -1 is going to look like -1 to the 5th minus 2 times -1 to the 4th. -1 to the 5th is -1 minus 2 times -1 to the 4th is +1. So -1 minus 2 is a -3. So actually, when x is -1, I should be way down here at -3. Huh. All right. How about x when x is -2? What is g at -2? Okay. -2 to the 5th is -32 minus 2 times -2 to the 4th is a +16. So -32 minus 32 is a -64. Holy cow. All right, well, I'm going to come back here. I'm going to edit this a little bit to where, yeah, it's going to come up here and it's going to touch, but then it's going to go down here and cross this point, and it's going to drastically head down toward the point -2, -64. I'm going to clean this part of it up as well. All right, let's get even a little bit better. What happens here when x is 1? When x is 1, g evaluated at 1 is 1 to the 5th, which is 1, minus 2 times 1 to the 4th is 1. So 1 minus 2 is a -1. So 1 -1, ooh, actually I might have dipped down just a little bit too far right here. It should be more along the lines of this, touch, down here, back up, cross, okay? And then maybe I want to calculate g at 3. All right, y'all, 3 to the 5th, holy cow, 3 to the 5th is 243 minus 2 times 3 to the 4th. 3 to the 4th is 81. All right, so we've got 243 minus 162. Okay, that is totally a point off my graph. I know that much. So I'm going to take that end behavior and I'm going to like take off. Okay? So this is a better sketch, more accurate of the polynomial function g of x. Okay? Now, let me label that. This is the graph of g of x equals x to the 5th minus 2 x to the 4th. Recall that we discussed turning points. Now, the turning points could be as many as 4. We only had 2 turning points, but that's okay.